Learn efficient pharmacology, Pharmacokinetics Part 14, Clearance. In the previous video, we have seen what elimination rate constant Ke is. The fraction of the drug eliminated in unit time. But Ke does not provide us information on efficiency of elimination. Why is that so? Because Ke does not account for the volume into which the drug is distributed. To understand the importance of volume, let's use this example. Imagine our body as a tub filled with 100 ml of water, divided into 100 equal squares, with each square representing 1 ml. Now, let's add 100 milligrams of a drug into this tub. The concentration of the solution can be calculated as amount by volume, that is 100 milligrams divided by 100 ml, which is equal to 1 milligram per ml. Thus, each square is 1 ml, and now it contains 1 milligram of the drug. The tub is connected to an eliminator box, representing organs of elimination, the liver and the kidneys. Elimination in the body we know generally follows first order kinetics, where a constant fraction is eliminated. Let's assume that this fraction is 5% per minute. That is, elimination rate constant Ke is 0.05 per minute. In the first minute, 5% of 100 milligrams, that is 5 milligrams, is eliminated. Here, 1 milligram is present in 1 square, so 5 milligrams would be present in 5 divided by 1, that is 5 squares. So, when 5 milligrams is eliminated, we can assume that the drug is removed from 5 squares. In other words, we can assume that 5 ml of water is completely cleared of the drug. Once 5 milligrams of the drug is eliminated, 95 milligrams of the drug remain. So, each ml would contain 0.95 milligram of the drug. In the second minute, 5% of 95 milligrams, that is 4.75 milligrams, will be eliminated. Now here only 0.95 milligram is present in 1 square. So 4.75 milligrams would be present in 4.75 divided by 0.95, that is again 5 squares. So when 4.75 milligrams is eliminated, once again we can assume that 5 ml of water is completely cleared of the drug. This volume, that is completely cleared of the drug in unit time, is called clearance. Here, the unit of clearance is ml per minute. To calculate the clearance in each minute, we divided the amount eliminated by concentration. Amount eliminated in each minute is in fact the rate of elimination. That is, we calculated clearance by dividing the rate of elimination by concentration. So in the first minute, 5 milligrams per minute divided by 1 milligram per ml was 5 ml per minute. In the second minute, 4.75 milligrams per minute divided by 0.95 milligram per ml was again 5 ml per minute. This is the exact calculation we did earlier in the first and second minutes. Now, if we continue to calculate the clearance of the drug in the tub using this equation, this is what we get. Here, clearance is a constant. This is because of the nature of first order kinetics, where, as concentration decreases, the rate of elimination also decreases proportionally. In first order kinetics, the rate of elimination is proportional to the concentration. If we introduce a proportionality constant, we have rate of elimination is equal to constant multiplied by concentration. Rearranging, you can see that this proportionality constant is in fact clearance. So clearance can also be defined as the proportionality constant that relates the rate of elimination to the concentration. If you ever forget this equation to calculate clearance, there is an easy method to derive it. We know volume is equal to amount by concentration. Therefore, volume cleared per minute is equal to amount eliminated per minute divided by concentration. Volume cleared per minute is clearance, and amount eliminated per minute, as we already know, is rate of elimination. Thus, we have clearance is equal to rate of elimination divided by concentration. Now let's go back to the tub. Imagine that instead of 100 ml, we have a tub with 200 ml of water containing the same 100 milligrams of the drug. Now the concentration is 100 milligrams in 200 ml, that is only 0.5 milligram per ml. Now let's again divide the tub into squares of 1 ml each. We have 200 squares and each square contains 0.5 milligram of the drug. Assume that the box still eliminates the same fraction, that is 5% in a minute. That is, the elimination rate constant Ke is again 0.05 per minute. So in the first minute, 5% of 100 milligrams, that is 5 milligrams would be eliminated. But now each square contains only 0.5 milligram. So 5 milligrams is contained in 5 by 0.5, that is 10 squares. That is, when 5 milligrams is eliminated, we have to assume that 10 squares or 10 ml of water is completely cleared of the drug. We can calculate this as clearance is equal to rate of elimination divided by concentration, which is equal to 5 milligrams per minute divided by 0.5 milligram per ml, which is equal to 10 ml per minute. So when the volume of the water was 100 ml, only 5 ml had to be cleared in a minute to eliminate 5 milligrams of the drug. But when the volume of water was doubled, to eliminate the same 5 milligrams, 10 ml had to be cleared of the drug. Even though the elimination rate constant Ke was the same in both cases, the eliminator box had to work more efficiently in the second scenario. So while Ke reflects the fraction eliminated, clearance also takes into account the volume and thus offers a more comprehensive assessment of elimination efficiency. How clearance takes into account both Ke and volume can be demonstrated from what we already know. We know that rate of elimination is equal to clearance multiplied by concentration C. In the previous video, we have seen that rate of elimination is equal to Ke multiplied by V multiplied by C. So we have clearance multiplied by C is equal to Ke multiplied by V multiplied by C. Dividing by C on both sides, we have clearance is equal to Ke multiplied by V. And now it is easy to remember how clearance accounts for both Ke and V. Now let's come back once again to this equation. Rate of elimination is equal to clearance multiplied by concentration. In the previous video, we have seen that the plasma concentration can be maintained at a steady state CSS when the dosing rate is equal to the rate of elimination. So here we can substitute rate of elimination with dosing rate and concentration with steady state concentration CSS. Thus we have dosing rate is equal to clearance multiplied by CSS. Thus, the dose required to maintain steady state plasma concentration, that is maintenance dose, depends on the clearance of the drug. Let's list all the aspects of clearance we saw until now and the relevant equations. Here, the rate of elimination, Ke, clearance, steady state concentration, and dosing rate have been discussed. Now let's focus on volume, V. To start with, our assumption was that the body was like a tub containing 100 ml of water. The drug was dispersed into this 100 ml. Here the total volume and the volume into which the drug was distributed was the same. There is no confusion, V was 100 ml. But in the body we know that drugs usually do not distribute equally into all tissues. So the total body volume and the volume into which the drug distributes are not the same. So then what exactly is V, or volume of distribution of a drug, Vd? We will see that in the next video. Here are some good to know facts. This is a summary of our discussion.